Hello again. We are going to be talking today about the least squares regression line and how we use it, how we don't use it, what the different parts of it mean, and how it's constructed. So what I have open here on my screen is an applet from the GeoGebra website. So there's a link to this on our Moodle page. Just below the guided notes. So you're welcome to sort of follow along, I guess, or just experiment with it at your leisure. So when you first open the applet, it's going to have a set of 5 data points, and you can drag these around so that you can make the points any shape that you wish. There's no real method behind this. I'm just moving them around a little bit. And then if you click on the right, you can make various things appear. Now the first one here, the show slope, intercept, and line, puts a line on the axes, and then it shows you the slope that it calls m. That's from the kind of standard form y equals mx plus b for a line. The intercept is the b. And you can move these around, right? These are sliders that you can left click on and drag, and then the line will move dynamically with your choice. So as I increase B, that increases the intercept. Notice that the slope of the line isn't changing, just where it crosses the y-axis as I move back and forth. And then similarly, I can change the slope. Right now it's got a positive slope of 1. I could increase that so it gets steeper. Or I can turn it negative right about there. So with a regression line, remember that the sign of the slope is the same as the association between the two variables. So a positive slope would mean a positive association between the variables. A negative slope would mean a negative association between the variables. Now, the applet is designed for you to kind of experiment to see if you can get the regression line correct. And the idea is to make the line that fits the data points the best. And now for the least squares line, what we mean by fits the best is actually a really has a technical meaning. So I'm going to click on Show the Squares, and I'll just point out that what these are, it's the square of each of the residuals. So if you look at this top data point, for example, right, the regression line that I've drawn anyway, it's not necessarily the line, but a line, it misses that point by a little bit. And the amount by which it misses the point is called the residual for that point. And a residual can be negative. If it's below the line, the point to its left would have a positive residual because it sits above the line. The line missed it underneath. Now the idea is to find the line that makes these squares as small as possible. Okay, so we've taken the residuals, we've squared them, represented by actual squares on the picture. And the larger the residual, the larger the square. So I could move my slope a little bit and make the last residual here really big. Now the reason we square them before adding them up and trying to figure out the minimum is if you just add the residuals together, the positives and the negatives cancel, and so you could have a really bad line that even so looks pretty good because the residuals would cancel, right? So that could sort of mislead us into thinking we have a good fit line when in fact it's pretty bad. But if we square all the residuals, add them up, and then try to find the line that minimizes the squares of the residuals, we'll end up with the best fit line, what we call the least squares, smallest sum of squares, regression line. So right now, the sum of the squares that I have drawn here is about 10. I can move the slope a little bit. Looks like I got down to, I don't know, about 9.4. I can try moving the intercept to see if that'll help. And And that is helping. I'm getting down to about 8.7 was about as good as I could get. Right about there. Try moving the slope again. And it looks like I'm not going to do much better, at least not right away, with better than 8.7. So I can click on Show the Actual Regression Line, and we'll see that I didn't do terribly. Right? It's not right on, but that orange dotted line is the actual regression line, and it's a little bit further to the right than mine was. Now, one thing that I also wanted to show was what happens when you move points around. So there's a discussion in the text about regression outliers. And what a regression outlier is a point that doesn't fit the overall pattern. Now, there's only so much we can do with, let's see, let me put my line back up. I think it's only basing this on my line. So the last point here on the right, we can move around a little bit, right? That fits the pattern better. I'm going to move these closer to the line. So I have a very strong linear association, positive linear association with these 5 points. But then if I were to move this point off the line by a fair amount, this would then be a regression outlier because it's really far from the pattern that's present in the rest of the points. Now, it's not necessarily an outlier as far as the x and y values go because it's right in the middle of the y values. It's a little bit outside the rest of the x values. We only have 5 points, so it's not easy to get a great example that way. But we also talk about outliers that are influential or not influential. So I'm going to put the actual regression line back up and show that if I tug this one down, right, notice how disturbed the regression line is. If I pull this point that's way out to the right down, the line tends to follow it. And because the line follows it and moves so much, this is called an influential outlier. Whereas if I took one in the middle and move that around, right, the line does move, but not nearly as dramatically as it did for the other. So this one would not be influential, even if it was kind of way up here and was something of a regression outlier. Okay, so I hope that helps visualize what the regression line does and how it's created. I'm going to move now to the example problems in the guided notes and see if we can make some progress on those. Right, so I've got a Word document here that I've got the picture from the notes, the equation for the regression line, and then we'll try to answer the questions together. All right, so the first one is, what's the overall pattern, and are there any striking deviations from the pattern? The pattern seems to be that as the years go on, the time for the men's 5,000 meters tends to decrease. There seems to be a linear negative association because the line is negatively sloped, right? And the dots go down as you move to the right. It's not particularly strong, so I would say maybe a moderate linear negative association. And there aren't really any striking deviations, although this point here at about 2012, that one's a little bit iffy, right? So if this was like a quiz problem and you flagged that point as being a striking deviation, or if you didn't flag it being a striking deviation, they'd probably both be okay. I would not call that a striking deviation. All right, so we've got moderate negative linear association, no striking deviations. It's not actually a complete sentence, but we won't be picky at this. All right, so what about the regression prediction for the time in 1968? Well, For that, we have to use the regression equation. All right, so, well, maybe I'll do it without the equation editor. All right, so we know that the prediction y is going to be 33.4 minus 0.01 times the x value, which in this case is 1968. So I need to do this on a calculator. Let me bring that up. And get it out of the way. So let's see. 0.01 times 1968 is 19.68. Make that negative and add 33.4. So I get 13.72 minutes. Right? So if you're making a prediction with the regression equation, what that means is you're plugging something into the regression equation. In this case, it was plugging in 1968. Now, in 1968, we actually have a data point, and that data point is this one here. And if I go across, it looks like the time in 1968 was about 14.1 minutes. So an estimate, just reading off the scatter plot, is 14.1 minutes. And then the residual is the difference between your y, your actual y value and the predicted. So keep that in red. 14.1 minus 13.72. So 14.1 minus 13.72. That's not what I wanted. I thought I was on the calculator. 14.1 minus 13.72, so 0.38 minutes is the residual. Don't need that. All right, now what about the y-intercept? Remember, that's the b in the ax plus, sorry, it's the a in the bx plus a formulation of the line. And so that is the value of y when x is 0. So if I plug in x is 0, what I'm left with is just this 33.4. So the y-intercept would be 33.4 minutes. And what this one means is the line predicts a time of 33.4 minutes in year 0. All right, so like a lot of intercepts, this does not make any physical sense for the problem. All right, so the meaning is with 0 years, you would get a time of 33.4 minutes, but it doesn't make sense in the context of the problem. All right, now what about the slope? All right, so the slope is the minus 0.01. So the slope is minus 0.01. And what that means is it's the change in y if x changes by 1. So if the year increases by 1, then the predicted time decreases by 0.01 minutes. And that's the same as, well, a minute is 60 seconds times 0.01. You move the decimal place 2 places to the left. So that's about 0.6 seconds. So we expect the time to decrease by about 0.6 seconds each year. Right? That does seem to make some sense, right? The record time should decrease, or does seem to decrease over time. What about 7? According to the regression, when was the winning time 13.75 minutes? Well, you can estimate from the graph, right? If we look at 13.75, it's about here, and then move over, we hit the line and drop down. That's about 1968 or so. Notice that when we found the prediction for 1968, it was 13.72 minutes, so that's awfully close. But we can actually solve by plugging in 13.75 into the y for our regression, and then we solve for x. All right, so 13.75 is the y, and so that has to equal 33.4 minus 0.01x. And so we can do this a couple of ways. Let me do the 13.75 minus 33.4. Right, so if I move the 33.4 over, I get a minus 19.65, and that equals minus 0.01 x. So x is 19.65 divided by 0.01, that's 1965. All right, does this make sense? Well, I think it does. We already kind of looked at the graph. 13.75 is right about there. It looks like it hits a little before 1968. So somewhere around 1965 would be that year. All right, now finally explain what the r squared means. Well, the r squared, that's just the square of the correlation. The higher the value, the better the line does at explaining the changes in the y variable as an association with x. And so a 0.48 for r squared, our interpretation of that is that 48% of the variation in y is explained by its linear association with x. So in the context of this problem, we would say 48% of the variation in record time is explained by its association with the year. All right, one last thing that we didn't say a lot about specifically in this example, and that has to do with extrapolation versus interpolation. So extrapolation is generally bad for regression, and that means that you are trying to use the regression equation to make a prediction that has an x value that's outside your data set. So we actually did one example of this in number 5, where we plugged in 0 to get the y-intercept and got a kind of a absurd answer in 33.4 for year 0. And that's because the year 0 is well outside the range of our data, which is from 1948 to 2016. So that's an example of trying to extrapolate from the data with a value that's way too far outside the range of the data. Right? If you plug in 0, you get a bad answer. Similarly, if we plugged in like the year 2500, right, we would get something silly in the end as well. Interpolation, on the other hand, is kind of what regression is for, and that's where you're making predictions amongst your data, right, in between your data, typically for places where you don't actually have a value. So, for example, it looks like we don't have a value for 1970. That would be a prime candidate for using the regression line because 1970 is inside of our data and we don't have a data point for it. So it would make sense to estimate what the world record time was in 1970 using the regression line. All right, so that's kind of the basics of linear regression. Hope that this made sense. If it didn't, shoot me an email or ask questions in class or visit me in office hours. So I will see you in class tomorrow.